So today we're going to move on with wavelets. So yesterday we started to look at wavelets from the angle from the filter banks, okay? And the idea was to say we've looked at the Haar transform as a two-point transform where we take, split the signals into pairs of samples. We apply the transform on each of these pairs independently. And then we say, well, actually, if you look at what the Haar transform does, the two operation it does to get the two outputs, really could be looked at as two different filters. And we designed these filters as being the average of the current pixel, if you wanted, the previous pixel, and the other one is like the forward difference between the current and the previous pixel. Then we say, okay, well, to reorganize these samples and to make it work, we need to, there's some kind of downsampling operation, and that leads to this, this graph, okay? This is called the analysis part. So you have your input signal that is split. We apply two different filters, so one is a low pass and one is a high pass, and then you apply downsampling on both of these outputs, okay? Right, so, and then we looked at the other part, which is the reconstruction, and we see that, okay, we can combine those by having this upsampling sphere. So remember, the upsampling is you insert zeros in between samples, and then you have this other pair of filters, which corresponds to your inverse Haar transform, and you will combine them by simply doing addition. All right, so this is the equivalent of the Haar transform. We say it's a two-band filter bank, and there's two bands because basically when you look at the frequency domain, one is low pass, so you keep the low frequency, that's your low pass band, and then you keep the second band, which is the high frequency ones, which would be H1. Okay, so you have low frequency going up and high frequencies going down. All right, so we looked at that and say this, what's going on here, so you have your signal filtered, you downsample, and at this point in the middle, what you have are the coefficients from your Haar transform, that's your transform, then you have the upsampling. And if we look at from a frequency point of view, what's going on here can be replaced by this operation in the Z transform, and I told you that this, when you access y of minus z, that really corresponds to a shift of pi in your frequency spectrum, and really what it corresponds to is the replication of your frequency spectrum. Right? So you look at your spectrum, you have, when you subsample, you have this replication, and this is the part of your replication here. This is the aliasing part. Okay. So what I said now was looking at is we've defined a number of filters. So we have this pair of filters for if you're on the forward transform, and you have this pair of filters for the inverse. And we wanted to know if there is, what kind of choices of filters could lead to perfect reconstruction of your signal. And I wanted to say that it's not obvious that you have perfect reconstruction, okay? So if you look at if you just have one band, okay, so you don't have two bands, okay, so you don't try to separate between high frequencies and low frequencies. So you just have your signal, you apply a filter, and then you apply another filter, and you want to reconstruct the signal. And in most situations, that would be actually very hard to design that. That is because, well, the first thing, like if your H0 is a FR filter, then G0 has to be 1 over H0, and obviously it has to be IR filter, so that's kind of not nice. And also, think about it, okay, if H0 is low pass filter, so we'll cut off some of the high frequencies, and these are lost, okay? So there's nothing that this filter can do to recover these lost frequencies. All right, so when you're in the one band case, if you apply distortion to the signal and try to distort it, well, there's a whole range of situations where that won't work very nicely. So really you need to be in this two-band system to be able to recover from the beginning. So let's come back to this diagram, okay? So let's try to see what we mean by perfect reconstruction, okay? So perfect reconstruction means that x hat here. So if you don't do anything with the coefficient here, so if you just do the transform and the inverse transform, you should come back on your feet. So the x hat here should be exactly the same as x, okay? And we're going to derive that from the z transform domain, okay? So we're just going to look at that in the z transform and see what the conditions on our filters are, so we can get that. So we know that x hat would be the sum of, because just addition here, so x hat would be the sum of y hat here, and so y0 hat and y1 hat, okay? So that we know, and then we have this part here, which is kind of the subsampling, desampling part, and then we come back. So this is what it looks like, okay? So we start from the end. We say the reconstructed z transform of x is as follows, and this is the result of doing the average, if you want, of the y hat 0 times the reconstruction filter you have on G0, and you do the same here, okay? So that is this first equation, that's this part here, okay? All right? And then remember, to go from y0, so we have y0 hat, and we have y0 here, and you have this subsampling, upsampling part in between. And we know what the effect of that. We know that the relationship between y0 and y0 hat is just this. You need to add this term of replication here. All right, so you have that, and then so you just develop, and you reorganize everything, and basically you have the exact equation. So from the transform of x, all the definition of all your filters, you get a relationship between what x hat is and x is, okay? And as you can see, there's kind of two terms that are interesting. So you have a term in x of z, and you have a term x of minus z. So this term in x of minus z, that's the aliasing part of the signal. Okay, so we know that this is the replication of your input. So we want, for perfect reconstruction, we want that factor here to be 0. All right, so we want to cancel that, to kill that off. We don't want any aliasing in the resulting signal, so we want to kill that off, which means that this part here must be 0. And similarly, we have a term here in front of, if you want a filter in front of x, and we want that part to create no distortion, so we want that part to be equals to 2. Okay? Does it make sense? We say that the output x hat, when we do all the derivations, is indeed a function of xz, so the input, but we want it to be exactly xz, okay? And for it to be xz, then this term needs to be cancelled, okay? So the last term here needs to be cancelled, and that's the aliasing term, so that needs to be, the green part here, if you want, needs to be equals to 0. And the blue part here must be equals to 2, so we can come back on our feet, okay? So these are the two conditions, okay? So the first one, okay, which corresponds to the part in front of x, is called the no distortion condition, okay? So we said that this product of polynomials must be equals to 2, and if we have that, then we know we don't distort the original signal. And the second part here, the green part, must be equals to 0, and that's the no aliasing condition, because if it's equals to 0, then we can cancel off the aliasing term x of minus z. All right. So we have a nice relationship. So we know if we design, if we find, so we have two pairs of filters to find. So the H0, H1, and G0, G0, G1. And if we can find, if I give these two, find these 4 filters in such a way that they satisfy these 2 conditions, then we know that we will be able to reconstruct the filters correctly. So that's interesting because that gives us a kind of a range of, a subspace of the possible filters we have. So let's look at the Haar transform and see indeed that it's correct. So the way you would do that, so that's used tend to be exam question. So you have a definition of your Haar filter. So this is the analysis filter, so H0 and H1, and then this is the reconstruction filter G0, G1. And well, all you have to do is to really plug in this polynomial Z in all these terms, check that indeed it's equals to 2 to check for the no distortion, and for the no aliasing, then you just check that it's 0. Okay, it's quite simple. In this case, it's working, so it's all fine. Okay, so indeed the Haar filter we have, and we knew that, right? When you plug it in, we know that it guarantees perfect reconstruction of your signal. All right, so let's go further and do as we did with Haar. So we know from Haar that what you can do is you can look at the low pass of your picture, or the low, and apply the same job, okay? And that operation, so the multi-level Haar transform, can be expressed here as a filter as well. So here's a system. So remember, we're working in 1D here. So you have your low pass H0, high pass H1, and at the end of this section, what you have is the results of the Haar transform of level 1 in 1D. Okay. But if we want to go to level 2, all you need to do is to apply the same filters on the downsample part, and you stop here. And what you have 3 bands, if you want, and that corresponds to the level 2. And then you can keep on doing that iteratively up to level 4. All right. So nothing, it's just a transcription of what we've seen in the Haar transform. When you work with the picture, remember well, maybe you don't remember that, but the Haar, the way we applied the Haar was we applied it separately. Okay, so we applied the Haar in 1D along the x, and then the Haar 1D along the y-axis, and that gave us the Haar in 2D. So similarly here, the way you express that, you say, if you just look at the rows, you have your picture as an input, and you're going to apply filters along the rows of your image. And you still have your 2 filters, the low pass H0 and H1, downsample, and then you're going to look on the columns of these results and apply the same filters along these columns. So here you had so it's a function of Z1 for the first coordinate, and now it's a function of Z2. And then you do the same. Okay, and now you have 4 outputs. All right? Okay, so this is just, rewriting that in these systems, rewriting what you've done already in these systems. If you have multi-level 2D discrete transform, this is what it looks like. And now, it's a bit scary, but it's basically the same what you've seen. So on this part here, you have the level 1. And the first pass here is for the row filters, and then the column filters. And then you have the 4 outputs from your first level. And then you look at the low pass, which is your Y00 here. And then you apply again the same transform on that. All right, so it's just diagrams expressing all that. All right, so the reason why we do all this is because we want to do, again, we want to look at the in analytic way the impulse response of a particular subband. Okay, so we want to see what the effect of taking that low, 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 or that low, 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 high, and so on. Okay, so we want to see what the equivalent Z transform of that particular path here. Okay, so that's kind of what we're interested in. Okay, so the trick here, okay, so the problem going back here is that you can see you have a lot of operation of downsampling that happens in between. Okay, so you have, if you only had these filters combined to each other, that would be quite easy. Just multiply all the transfer functions, and that would just be fine. But the problem you have this downsampling by 2, which cause problem in the analytic derivations of your system. So the trick here, okay, so you can look back at the notes, is this equivalence, okay? So the problem we have is that you have a downsampling operation followed by a transfer function. And it turns out that this is equivalent to, you can flip both operations and have the filter before and downsampling after. But what you have to do is to take care of that is to change the impulse response, if you want, of your system and scale it. So what you do is you replace h of z by h of z squared. So h of z squared, if you think about that, that means that we're going to consider, it's kind of a zoom on your transfer function, and instead of taking samples from 1, 2, 3, 4, it's going to take samples from 1, 4, 6, 8, and so on. I'll leave you read into this computation at some point, okay? But it's not hard, okay? It's just basically the when you look into it here, you see you have a z to the power of minus n in your z transform, and when you square it, now also you have z of minus 2n. Okay, so this kind of downsampling operation means that you go from n to 2n. That's a subsampling. That kind of is, that's why you have a z square. Okay, the z square corresponds to your downsampling operation. Anyway, if you do that, then what it means, you can flip all this downsampling operation and have them all at the end. Okay, so what I've done here is moved all the downsampling that were after each of the filters and just moved them back to the end. All right, so now we have a cascade of filters, but I had to change the filters. Okay, so now the polynomial, the z transform is not h of 0 of z, it's h0 of z squared. And here it's h0 of z4, h0 of z8, and so on. But the good thing is, the downsampling operation is really much at the end, pushed back there. All right? Which means that I can analyze what's going on here by just saying this is just a multiplication of all these particular z transforms of the transfer functions here, and I'll get a pretty good idea of what the transfer function for that particular subband here. Does it make sense? It's just a little trick to help you analyze what's going on in terms of z transform per subband. All right, so an example. So if you look at the transfer function for the low, low, low pass, so the low pass at level 4, so that's h0000z, and that's just the multiplication of all these subbands here. Okay, and that's before I subsample. All right, so you can just, that's quite straightforward. All right, so if you look at, so if you just take one example, so this lowest band, okay, so if I replace all the, if I apply this, see, expand from here, okay, so just expand what it is for the Haar transform, then you see that, and this, what you see is just the sum, so the low pass, okay, kind of makes sense, it's just the, at level 4, is the average of 16 samples. So you take 16 samples and you just average those in a row. Okay, so it's a low pass filter with a mask of just ones everywhere. Okay? So this is a more kind of graphical way to represent that. So going from the Z transform to the impulse response in terms of the discrete representation. So this is your impulse response of the low pass of the force level. And you can see here you have these 16 values of, so it's 1 of the center and then 0 everywhere. Okay, so you have this low pass. It's just a pulse, okay, of size 16. If you look at the other ones, something that kind of is striking is that the shape is more or less the same. Okay, so the shape, if you look, the shape of this little, it's called actually wavelet. Okay, so the shape of this little wavelet is rescaled through the different bands. Okay, so the wavelet has the same shape. Okay, so the impulse response are the same shape, except somehow it seems that it's kind of stretched. Okay. On the right here, you can see the frequency responses. So if you look at the low pass version, this is H000, and it goes down as a sinc function. Okay, and that's because it's a pulse, so rectangular function, so you will get a sinc at the end of it. Okay, but you can see H1. It's more kind of a high pass filter, and it will cut off the low frequencies, and this is the response for H1. Okay? So the process of creating all these guys, okay, is called the discrete wavelet transform. Okay? And that's what I said. So all these shapes are kind of similar, and they all derive from something called the Moser wavelet, which is the kind of original shape of that transform. We'll see different types of transform. Okay, so this looks this way for the hard transform, but we'll see for different types of wavelets. So then comes, okay, so we know from the perfect reconstruction how these filter bank, these filters could be designed. And so we know how to derive a discrete wavelet transform from this choice of filters. So now the question is, can we use different filters from the hard filters, because we know the hard transform is the simplest one you can find, but maybe not the best. And the answer is yes, you can design, and there's been a very large body of work on the domain on trying to design what the best filters are, and the argument usually goes as follows. You kind of you set a nice relationship between your H1 and your G0, and your G1 and your H0. And you do all sorts of tricks, and then you go on and forth, and you find families of functions and design and so on. But it turns out it really depends what the application should be, what the desired properties of your system should be. All right? And it's quite, so the whole families of different wavelets, and they all have all slightly different properties and so on. So let's look at some different types of wavelets exist out there. So this is called the Legal 3-5 tap filter set, and because it was first written by Legal discovered by Legal in 1988. So the filters then, if you look at the definition, they use a bit more taps. Okay, so for the hard filter, you only use the current sample and the previous one. Here you need at least 3 samples to be able to take a decision. So you have 3 taps, so it's slightly larger. So that's the definition for H0, G0, G1, H1C. You can do the maths to check that the perfect reconstruction holds and that everything is fine. And this is what, when you apply and trying to get the inference responses for all the levels, this is what you get. Okay, so this is the shape of the wavelet, and you can see again through the different levels, this wavelet, kind of the shape, you know, it's called the mother wavelets. You can see that the shape really is more or less the same, it just gets stretched somehow. This actually is called the scaling function as well. Okay, so scaling function, if you only have all the high pass versions, and you have the low pass, and the low pass has a special name as well. So you can see the frequency responses are maybe a bit more interesting because I don't know if you remember the Haar transform. In the frequency domain, because of this, the discontinuous nature of this one, because you're looking at rectangles and so on, in the frequency domain you have all this, it's a bit crazy going on, okay? And that's because of all the sinks function going up and down. With the Legal filter, it's a bit cleaner in the frequency domain, okay? All right, this is the inverse Legal. So it's an interesting point, okay? You can, so coming back here, sorry. So here, as it turns out, you can swap the G's and the H, and it still go fine. Okay, so you can swap things around. So you can, you have your analysis filter here and your reconstruction filters, where you can swap those and reuse the reconstruction filter for analysis and so forth. Okay. For the Haar transform, it makes sense. Remember the inverse of the Haar transform itself. Okay, so that kind of makes sense. Anyway, so this is the Legal filter when we swap the things around, and the shape is slightly different. As you can see now, there's the mother wavelet has kind of a funny shape really going on. With like 1, 2, 3, 4, 5 points on here, and this is the frequency response for those. Right, so if you look back at the 3.5 filters, they're quite smooth in nature, okay? So the filter itself is quite smooth, so they can be used for analysis, okay? So the idea would be that, so I talked about that a bit, okay? So the idea is like, okay, if you want to go beyond, say, if you want to go beyond compression, and maybe you want to transform your picture and get some useful information about the picture, okay? So for the people who have done deep learning, that would be the trying to apply all the filters, like all the convolution layers, gives you features that are interesting to analyze, okay? Here would be to use this particular filter bank, you apply this transform, and what you get at the end is transform image where the information in the bands is maybe more useful. So maybe you want to do image detection in that space rather than the input space. Well, it turns out that here it's interesting because the analysis filters are quite smooth, so therefore the analysis you get is quite robust and quite useful. But if you use these guys, which are much less smooth, then the analysis will be very much, like if you add a bit of noise to your picture, the results will be vastly different, and you have lots of variations in your features. So anyway, the smoothness of the filters has an impact. So here's a whole bunch of different filters. And remember, like you have the analysis filter and the reconstruction filters, and they're different, right? They can be different. So there's a whole class of wavelet wavelet families where they're trying to match the reconstruction filters to the analysis filter to make them as similar as possible. So here's an example of the near balanced 5-7 taps. And so you see the analysis filter and the reconstruction filters, they're almost identical, but they're not exactly the same, okay? So they're almost the same, but not quite the same. So larger taps, so the more taps you have, the more interesting things you can do, but then of course, it takes more time to compute. This is a 2D view of what these filters look like. So if you had to apply convolution to get the same result of the filter, this is kind of what you get. So on the left, you have the 4 masks for your so low, low, high, low, low, high, 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 if you want, okay? So this is what the mask look like, okay? So here you have a low, low mask, and you can see a bulge in the center, so that's kind of the low pass filter. It's a bit like the Gaussian filter you applied, remember? Okay, so you kind of have a smooth, you weight the values around the mask, centered in 0, and as you go further away from the central point, the weight tails off, okay? Anyways, this is kind of an example of what we get. Okay, so it's quite a lot of information here, but basically, the argument goes as follows, okay? All what we've seen with the Haar transform can be expressed in these systems with filters and downsampling and upsampling scales. Using a few tricks, we're able to re-express those and try to see first what kind of filters we can use. And we've seen there is this condition for perfect reconstruction, which gives us 2 conditions, okay? So there's the no aliasing condition and the no distortion conditions, okay? So 2 equations we have to say if your filters satisfy these conditions, then you can do, they can be used for wavelet decomposition. And then we've seen how the multi-level Haar transform we've seen can be expressed as a discrete wavelet transform, all right? And that's pretty much it, okay? So, all right, so what do we get here? Right, so more examples. 2 seconds. Okay, so what we're doing here basically is apply this discrete wavelet transform, so that just keep in mind that's the same stuff you've done with the Haar transform, with just different filters operations, okay? So on the left you have 8x8 DCT with quite a heavy quantization. The root mean square error here is at 10.49. So that's the objective quality metric. And for kind of similar error, this is the Haar transform that we looked at. Okay, so the entropy was a bit worse than for the DCT. But these are for similar quality what you get with legal 3.5 and legal 5.3. So you can see here the inverse legal, so when we swap the reconstruction and analysis filters, the results are quite good, okay? So you don't see, I mean, you lose a bit of texture, but the surfaces are much smoother than they were even with the DCT, okay? So DCT, you have all these blocking artifacts, okay? So because you look at blocks of 8x8, and you don't have any continuity in between the blocks, then you get this kind of banding artifacts, okay? But if you look at the inverse legal, you can see everything here is smooth and kind of looks nice, okay? And that's because here we didn't split the picture into blocks of 8 by 8. We actually applied this kind of continuous, we looked at the picture at different scales and we combine all that so you can capture all the very smooth changes in the gradients and so on. The importance of which filters you use in which order and how smooth they are is important because, see, this is the legal 3.5 and this is the inverse legal 5.3. And as it turns out, if you use one or the other, like if you swap them, things go wrong here. And that's because if the inverse filters are not smooth, when you quantize, you create some artifacts, okay? And so if the apply non-smooth filters on the reconstruction, then all the errors will be more pronounced. Okay? So usually what you want to have is reconstruction filters, so your G's, okay? So your G of 0 of Z and G1 of Z, you want them to be quite well behaved and reasonable in shape, okay? And this is the 5.7 filters and 13.19 filters here shown. All right, so usual graphs you have seen. So we're looking at 5 different types of compression. So first one is har, and you have the entropy on the y-axis. So entropy, so number of bits per pixel, and so har is around 3.7, I think. And then you go down as you go along with a bigger and bigger filter. So you can see this quite, I mean, we've seen that on the picture, but going from har to inverse legal, you do visibly a better job, okay? So pictures are better suited, it's better suited for picture compression. All right, so, what time is it? Okay. So it's all nice, okay? So we compared for a particular level of compression, for a particular Q step, we compared the different wavelets, or we can even compare to DCT and so on. But usually that only tells a story for a particular value of the quantization, okay? So it's not, if you apply a Q step of 50 on the DCT, maybe we look good, but maybe because everything is scaled differently, the wavelet transform, maybe the same Q step of 50 will give you a poor results. But maybe if you take a Q step of 20 on the other wavelet, then maybe it'll be better and still lower entropy. So the point I'm trying to make here is like, it's easy to always find, to tune your Q step to find one algorithm to be better than the other. So what you need to look at is actually take multiple samples to vary your Q step, okay? And so what you need to look at is something called the Red Distortion Curve. So what do we have here? Okay, so we have a graph. So on the x-axis, you have the entropy, basically, and so in bits per pixel. And on the y-axis, you have some measure of quality. So in this case, would be the root mean square. So that means that you want to be closer to 0. Okay. So when you look at a particular algorithm, so say your har transform for a particular quantization step. Okay. So that's one algorithm. So you set your Q step and you use your har transform. And when you apply it on your picture, what you will see is you get a point, and the point will say, for instance, I'm here, I'm 0.1 in bits per pixel, and I've got a root mean square of 2. So that's kind of what you get. So a point on the curve is applying your algorithm for particular settings, okay? So especially for the Q step. So that means that to analyze the performance of a class of a particular algorithm, what you can do is to say, well, here's my picture. I'm going to apply different Q steps. So I'm going to try different values of Q steps. And I'm going to look at the results. And to make to go through all the possible values of Q steps gives you multiple points on this graph. Okay, and so here, for instance, I have two techniques. Say DCT and R. Okay, and for both of them, I'm going to apply different values of Q step, and I'm going to see where they fall in that graph. Does it make sense? All right. So where you want to be is here. Okay, so you want to have a very low entropy and a very low distortion. So you want your picture to look still pristine and to have somehow find a magical way of getting almost zero entropy. All right. So this, the lower left part here is very good, and here it's pretty poor. So you have still a high entropy, and the distortion is very poor. Okay. So the way you compare this algorithm is not in isolation. It's not just for one particular point. It's for the entire curve. And now you can see these two methods, for instance, that on this section, if you want low entropy, so if you want heavy compression, then maybe you want to use method 1, because that's what gives you the best distortion. And if you don't require to have such compression rates, then maybe you should use method 2, because method 2 seems to do better in terms of picture quality for lower compression rates. Okay, so these red distortion curves are important, and there are, it's a kind of stuff like, it's equivalent to the RC curves you will have seen, some of you in the machine learning course. Okay, so you usually don't look in isolation at just one particular result. So we do the same here. So on the x-axis, you have the entropies, and you have the distortion on the y-axis. So here we didn't have much opportunity to do that for more than 2 points, but try two different quantization steps. And so there's you don't really have a curve; it's more like a segment. But still, it's useful to have a good idea of how the algorithm performs. So this is the Legal, the Haar transform, the I by DCT, and the inverse Legal, this and so on. Okay, and basically you can see. So okay, the closer you are from this point here, the better you are, and the further away you are, then the worse you get. So you can see here clearly that the say 1319 tab discrete wavelet transform is actually much better than even the by DCT or than the Haar transform. Okay. So now you kind of have a proper objective metric on how well you're doing right there. This is a graph from an actual paper on JPEG versus JPEG 2000. So JPEG is using the 8x8 DCT, okay? And JPEG 2000 proposed two filters, so the 9.7 and the 3.5 filters you can choose from. And so basically JPEG 2000 uses wavelets, okay? And JPEG using DCT. And this is the same kind of graph. Now the rate is the same, so it's still the entropy. The difference here is like express the distortion as the PSNR, so the scale is changed, okay? So it's flipped, okay? So now you want to have the highest possible. So a PSNR 40 means you visually don't perceive much difference, okay? So the higher you go, the better you are, okay? So it's kind of, that's flipped. So where is the JPEG? So JPEG is the P and the, so P is for progressive and sequential, but it doesn't matter, okay? So PDCT and SDCT, and this is where your points are, okay? And all the other points are your JPEG 2000 using wavelets. So clearly, at any given rate, so any given compression rate, the DCT offers a lower PSNR, than the JPEG 2000. So it means that JPEG 2000 is actually better than JPEG at any compression rate. Okay. All right, so that's kind of it. So it's quite a lot, okay? But this is kind of what you have to keep in mind, okay? We've had this class of transforms, if you want, for us, derived from the Haar, multi-level Haar transform, and you can express that as this, these systems of filters. And we found a way using a number of tricks to see how to express directly the transfer function for each of these bands, okay? So we're going to, after the transform, we're going to get multiple bands for different frequencies. And you can see, you can derive exactly what these bands, these responses are. When you look at that, okay, you can see why they call that the wavelet transform. It's because basically you have a shape, the original wavelet, you can see here, that gets kind of scaled at different levels, okay? And this is kind of a multi-level, so basically that's what you have. You have your impulse response for that particular filter get expanded at different levels, okay? We saw with the perfect reconstruction that there is actually, we can define a whole bunch of different types of filters that will still work in that framework. And so we looked at the no aliasing condition, the no distortion condition. And then we looked at a whole bunch of these filters and how they work. And in particular, here is the Legal filters and the inverse Legal filters. Okay? Using the right set of filters allow us to get better reconstruction, and we've seen indeed that at the end of the day, you tend to get much better results than in DCT. And one of the particular noticeable artifacts you will see in DCT is block effects, because you look at a transform over a little 8x8 block. So when you go across blocks, you would see bonding artifacts here. Whereas with the wavelet transform, you don't get that. Everything is smooth here. It's a bit more natural. Okay, and not only looks better, but actually in terms of statistics, image statistics, we can see that indeed these DWTs, discrete wavelet transforms, give you better transforms than just the DCT or even the Haar. Okay. So that's it for wavelets. All right.